Welcome back, Algebra 3. We are in Lesson 5. We're going to start talking about exponents and radicals. You know how addition and subtraction are opposite operations, right? And they cancel each other out. So if I were to say 8 plus 4 minus 4, that's 8, right? Because these are the same, they cancel each other out. And if I were to say 8 times 4 divided by 4, they would cancel each other out. It's the opposite operation. So we know that's 8. So in much the same way, exponents and radicals do the same thing. Let me illustrate that by saying if I have the square root of 4 times the square root of 4, we know the answer is 4. We know that. We've proven it. We know that the square root of 4 is 2 times the square root of 4, which is 2. So 2 times 2 is 4. But what we're actually seeing happen here is we know that the radical index, when it's not written, it is by default 2 here. So right, so we'd have a 2 and a 2. And we know that when a number is used once, it has an exponent of 1. It has that invisible exponent of 1. It just tells us how many times that number is being multiplied. And when we have the same number multiplied times itself, we can add those exponents together. That's the rule of exponents. The same base multiplied times itself, we add them together, we get a count, and that is the exponent that's being used. So what we're actually seeing here is the square root of 4 squared. And when the index and the exponent match, they cancel each other out. So you're just left behind with the number. I could further illustrate that by using the fractional exponent. The fractional exponent here, we put the exponent of the number over the index of the radical, right? The exponent of the number over the index of the radical. Well, we know when we multiply two like bases, we add the exponent together. Here, the exponent just happens to be a fraction. So when we add 1/2 and 1/2, we get 4 and 2 over 2. Well, that equals 1. 4 to the 1 power, it's just 1. So whether you do it like this or like this, we're still saying the same, it still has the same rules and properties that make it come out to the same answer. So likewise, I could say 5 and 1/3, or to the 1/3, times 5 to the 1/3, times 5 to the 1/3, would give me 5. 3 over 3 would just be 1. So the answer is 5. And that is the same thing as saying the third root of 5 times the third root of 5 times the third root of 5 is equal to 5. Well, I mean, what we're really looking at is we're saying the third root of 5 to the third power. The two numbers cancel each other out. Just like here, you would actually have 3 over 3, which we know equals 1, so the answer is 5. So you can see how both ways work and how we can convert the radical to a fractional exponent to help simplify and clarify what we have and condense it down into one number. It just makes it a little bit easier when we put it in that fractional exponent form. So let's try an example problem. Let's do 5.1. You jump in here. And I'm going to, as I write it, you write it, and we'll work it together. Let's see, x cubed, y. And this one is the fourth index of x, y cubed. So the first thing we do is we replace the radical with parentheses, right? And we put this here, x3y, and then this is a square root because there's no number. So we put the exponent 1 over the index of 2. So for this one, we put a parenthesis, we write what's on the inside, we put the index and the exponent because we're writing it the same way it is here. You're going to have an exponent of 1. Now all we do is multiply the exponents times the exponents, right? And we remember that this has an invisible 1 and this has an invisible 1. So this becomes x and 3 over 2. This becomes y 1 over 2. The second parenthesis becomes x 1 over 4 and y 3 over 4. Easy peasy. Now all we do is combine them together. And the way that we're going to do that is by making sure they all have the same denominator. So we're just going to rewrite this one as 6 over 4 just to change the denominator. It still has the same value. And we'll do the same thing here. And that one will become 2 over 4. Now they all have the same denominator, and we can easily combine the x's and the y's. X would become 7 over 4, and y would become 5 over 4. Sorry, I was looking, and I'm like, where's the other y? I kept coming back to this one. My brain wasn't working. So x and 7 over 4th power, y and to the 5/4 power would be our answer right there. All right, let's do example problem 5.2. We're getting progressively more difficult as we go along. And this is a fractional exponent. And then here we have a operation exponent with a fractional exponent on the outside. And that's all over AY on the bottom with their own set of exponents. So the first thing that we need to do is write all the exponents in the numerator. And the reason we can do that is because these are all factors. They're all being multiplied against each other. All right, we can only do that when everything is being multiplied against each other. We don't have any other operations going on here. It's all multiplication. So that allows us to bring these to the top and just change their signs. So when I rewrite this, I'm going to do all the math as I need to. So first of all, I'm going to release the x here. I'm going to say a and 1 over 2x. And that's easy enough to do. It makes it just easier to understand what you're working with. Then I'm going to multiply 1/2 times 2, and I'm going to say y 2 over 2 minus 1/2 x. And I've done the multiplication there. So now I have my denominator of 2 here. Now I'm going to bring this to the top and make this a negative. So this is going to be a to the negative 3x, and then this would become a positive, so y and a positive 2x. All right, so I want to be able to combine these bases that are alike. In order to do that, I've got to have a common denominator here. So I'm going to rewrite this as negative 6 over 2, because that still has the value of negative 3. And when I combine this, I get a negative 5 over 2x. All right, and then the y, in order to combine those, I'm going to need to turn this into a fraction with a denominator of 2. So I go 4 over 2 because that still has the same value as 2x. And I can combine this x term with this x term. And because this is the base, because it is an exponent, we want to write it as simplified and succinct as possible. And that means we really don't want to have an operation in there, or we don't want to have, we do, an operation is fine, but we don't want to have an operation in two fractions. We want to write it as one piece, one fraction. So we are going to write 2 and negative 1x, positive 4x would be a positive 3x, and all of that over 2. That's the most succinct way that we can write that exponent. Now we could do 2 over 2 is 1 plus 3 over 2x, but that kind of defeats the purpose of writing it as one item or one unit, right? It would still technically be correct, but this is what we prefer. All right, and that would be your answer. Some people, I want to just draw your attention, sometimes the book is going to put this and this in parentheses. It's okay if they do. It's okay if you do. And sometimes it's just to make it more clear that this is an exponent for this base. And that's the only reason that they do that. So if it is written like that, if you see it like that, it's fine. But if you see it written where it's clearly superscripted and above the base, that's all that's important, is to make sure that you write it so that you know that it's an exponent. That's the important thing. Okay, let's do example 5.3. And this one, again, a little bit more complicated than the other one. That's a -2 as well. And that's over xy to the -1. All right, so our instructions say to simplify. We are going to begin, first of all, by getting rid of the negative exponents. And because we have the operation here, it's not multiplication. It's not factors. This addition means this is the entire value. It's a whole value here. So we have got to eliminate our negatives a different way. And we're going to do that by turning these into individual fractions. So then we have 1 over x squared plus 1 over y squared. All of that over 1 over xy. Okay. We still can't just bring this up here because we have two different fractions, and we can't do keep it, change it, flip it if we have the same fractions, or the two separate pieces here. So we need to create one fraction in order to keep it, change it, flip it, to get rid of the division between these two fraction sets. So in order to do that, we're going to multiply by the opposite denominator, just like you would in any other fraction. So this becomes y squared plus x squared over x squared y squared. And then it's still all over 1 over xy. Now we can do keep it, change it, flip it. So we'll do y squared plus x squared over x squared y squared times, and we flip this, xy over 1. Now, before we go any further, we can actually factor some things out. So what we're going to do is we're going to factor out an x here and an x here, and we have one x left behind because we got rid of one of them. We're going to factor out a y here and a y here, so we just leave behind one y. So now that we've done some factoring, we can do the multiplication. We got everything factored out. So this is going to be y squared plus x squared over xy. And that's where we are. That is our final answer. So remember, if you have an operation, we have to create a fraction, right? We have to figure out how to make that a fraction in order to do simplification. And because these were negative exponents, we had two fractions, two values with this operator. We couldn't just go straight into flipping because it wasn't all factors. All right, so let's look at example problem 5.4. So we have a doozy here. We have 3 times the square root of 3 over 2 minus 4 times the square root of 2 over 3 plus 2 times the square root of 24. All right, so what we need to do here is simplify. So we know that we can break this down and say 3 times the square root of 3 over the square root of 2. And we know we can get rid of this denominator radical, which we do not like, by multiplying the top and the bottom by the same number, which in this case is going to be the denominator. So that's going to give us 3 times the square root of 6 over 2. We're going to do the same thing here. We have 4 times, or 4 and the square root of 2 over the square root of 3. 4 times that. And we're going to multiply times the denominator on the top and the bottom. So that's going to give us 4 times the square root of 6 over 3. Now we need to simplify this. Now what I could do here is factor out 24. And I know that that's going to be 2 times 12, which is 2 times 6. And I know that 6 is 2 and a 3, so I can't factor anything out there. So that becomes a 2. 2 times 2 is 4 times the square root of 6. Now I need to get everything into the same denominator. So what I'm going to do here, obviously these are 2 prime numbers, so my denominator is going to be 6. So I'm going to multiply this by 3. That's going to give me 9 times the square root of 6 over 6. Minus 2 times this will be 8 times the square root of 6 over 6. Plus 6 times 4 is 24 times the square root of 6 over 6. Now I can combine all of these since they have the same denominator and the same base radical. 9 minus 8 is 1 plus 24 is 25 times the square root of 6 over 6. All right, let's begin with example problem, or let's finish this with the example problem 5.5. This one's a little bit more complicated. We have the square root of 2 plus the square root of x multiplied by 1 minus the square root of x. And we need to simplify this. So we're just going to do the regular distributive property multiplication. If you want to stack it, you can. But I'm just going to do the rainbow like we normally do. Square root of 2 times 1 is just going to be the square root of 2. Square root of 2 times a negative square root of x is going to be minus square root of 2x. Square root of x times 1, that is going to be plus square root of x. Positive square root of x times negative square root of x is going to be negative x. So now we can look at what we can simplify here. And the only thing I see here is we can factor this. So this becomes square root of 2 times the square root of x, which means that we can then factor not negative, but the square root of x out. So we would say the square root of 2 minus the square root of x times, actually that'd be positive, negative square root of 2 plus 1 minus x. And if you want to, if you don't like that negative square root of 2, you can always just rewrite that and say 1 minus the square root of 2. It's the same thing, it's just less complicated looking this way. And if the whole point is to simplify, then why not write it that way? Right? All right. So we know that the coefficient of the second term is the sum 1 minus the square root of 2. All right, moving on. I'm going to clear the page. In mathematics, we use the letter I to represent the positive square root of negative 1. Basically, I is equal to the square root of negative 1. So that being said, we know that I, excuse me, too much talking, I squared is going to be the square root of negative 1 times the square root of negative 1, which is going to equal negative 1, right? Makes sense. The square root of negative 1 is encountered often in the solution of the quadratic equations. And this shorthand symbol for the square root of negative 1, the I, was first used by some guy in the 1700s, Leonard Euler. And it may be that I was first used to represent the negative square root of negative 1 because I could be written with one stroke of the pen if the dot is neglected. And for the most part, mathematicians like to shorten things up, and this is a lot quicker to write than this, so he just used that letter. And we don't really use that letter for anything else as a variable because it looks too much like a 1, but also because of the designation that it has right here. All right, so let's look at an illustration of this. If I had the square root of negative 13, I could factor that out and say the square root of 13 times negative 1, which we know we can break down into the square root of 13, square root of negative 1, times the square root of negative 1, which would be the same thing as the square root of 13i. And that I, note, is on the outside of the radical. It's not underneath. It is on the outside. That is the correct way to write it. So whenever you're typing something in Jupyter, don't do it like this. That's incorrect. You really need to do it like this. Okay? Make sure it's not under the radical whenever you type that in. A complex number is made up of two real numbers, a and b, and the letter I. And we always write that in the standard form, a plus bi, meaning that whatever number has the I, it is written second. Okay, that term, the I term, is always second. That is the way that we like to see it. The way that, because it's not really a real number. It's the square root of negative 1. Can't really, express that. So because it is an imaginary or complex number, it has to be written second because we want our real values to be first. Okay? All of the following numbers are complex numbers in the form a plus bi. And I'm going to show you what I mean. 4 plus 2i, that's obvious. 3.01 plus square root of 2 over 3i. That one's pretty obvious. 4.06. It is written in that format. It would have been like this, plus 0i. So 0 times anything is 0, so we don't write it. 3i, there is no real value in front of it, so we can only express this. That'd be like saying 0 plus 3i. So because 0 has no value, we just don't write it, right? So be aware of those things. And also, we have 13, the square root of 13 over 5.6 plus the square root of 2i. Even though we have a radical here, and we always write our radical second, if you have a radical and a complex number here, then this one comes second, okay? This is always second, or I should say last, whenever we write these numbers. So let's do example problem 5.6 and kind of just review this. We have two of these to review. So 5.6 is 3i cubed plus 2i to the 5th power minus 3i plus 2i squared. So first of all, let's get rid of any of these that we can. So this is going to be 3 times negative 1 times I. Because I squared is negative 1, we can get rid of 2 of these by turning it into a negative 1. Plus 2, now we have 5 of these, so it's 2, 2, and 1. So it's negative 1, and I. minus 3i plus 2, and we have 2 of these, so that's times -1, right? So now let's do the math that we have broken it down. That's -4i, and this is 2 times -1 is negative. Negative times negative is positive. It's still going to be plus 2i minus 3i minus 2. So I have -4 and a -3. That's going to be a -7 plus 2. So it's going to be -5i minus 2. Well, I has to be second. So this is going to be -2 minus 5i is the correct answer. I think I did that right. My book does not have that answer. Let me see what I did. So we had, oh, I see what I did wrong. Totally messed that up. This should be -3i. I added and multiplied and did something wonky all at the same time. So this should not be that. It should be 6 plus 2. That'd be -4i minus 2. We know the real number comes first, so it's -2 minus 4i. That is the right answer. All right. All right, so sometimes you have to go back and check your work, just like Miss Tracy does. Let's look at 5.7. Let's simplify -3. Square root of -3 times the square root of 4 plus 3 times the square root of -2 times the square root of -9 plus square root of -16 plus square root of 16. All right, so we begin by using the I notation. So we start here with the square root of 3 times I, and we know that this is 2. So the square root of 4 is 2, so we can write that right in front of here. 2 times the square root of 3, I. Now let's look at this one, plus. So we have 3 times the square root of 2, so we know that that's going to be 3 square root of 2, I, because it's a -2. And then this is going to be, we know that 9, square root of 9 is 3, so that's 3, and then we have another I. So 3 times 3 is 9, and I times I is -1. So 9 times -1, that's going to be a -9 times the square root of 2. All right, and now let's look at this. We know that we have a square root of 16 is 4, and then we have a negative, so that's an I, and then we have a positive 16 square root, so it's going to be 4 plus 4. So that is our result. Let's see what we can combine, if we can combine anything. We cannot combine anything, but we can factor some things here. So we could put our i's together. Let's see if we can do 2 times the square root of 3 times I plus 4i minus 9 times the square root of 2 plus 4. We can do this in 2 parts. We can say I. Actually, we wouldn't say that. We would say 2 times the square root of 3 plus 4 times I. We factored the I out. And then that is going to be plus, and we want to have this as a second number because it's a minus sign, 4 minus 9 times the square root of 2. And because this is an I, we want to move that. That has to be in the back. So our answer is going to be 4 minus 9 times the square root of 2 plus 2 times the square root of 3 plus 4 times I. All right. So this would be our A value. This will be our B value with I second. So let's talk about areas of similar geometric figures. Mostly we're going to talk about ratios and scale factors when we look at these two things. And we've gone over ratios and square factors before. Let me put example 5.8 up here for you. And that'll be a little bit easier for you to see the illustration. So here we have something that isn't a rectangle. Let me make it a rectangle. It's supposed to be a rectangle. All right, and now I'm going to copy and paste this. Now I'm going to enlarge it a bit. All right, but we know it's the same shape as far as it's a scaled up version of this shape. And we're going to say that it is 4 times the size, right? So the length here and the width here. The area of this is area 1 and the area of this is area 2. And we have a scale factor of 4 here. So whatever this length is, 4 times that is this length. Whatever this width is, 4 times that is this width. So area 1 can be written as length times width, and area 2 can be written as 4 times the length times 4 times the width, which would equal 16 times the length and the width. So we can represent that ratio as area 1 over area 2 would be equal to the length times the width over 16 times the length times the width, which would give us a scale factor here of 1 over 16. Because we know there's always an invisible 1 in front of our variables here, that gives us that. We can factor LW and LW out and leave behind 1/16. So that is our scale factor of area 1 to area 2. Area 1 is 1/16 of area 2. Or you could say 1 to 16 as you see fit. So let's try another one. And it's going to take me a second to get it up here. Let me pause. So here we have some circles. Here we see the radius of one circle is r. And the radius of the second circle is 3r over 5. So we are asked to find the ratio of the area of the first circle to the area of the second circle. So first we're going to write this out. Area 1 over area 2. Just so we can keep it straight in our head. This is going to be area 1 and this is going to be area 2 because it says the first one to the second one. All right, so now we're going to put in our formulas. Pi r squared, and the r for the first one is the capital R. And that is going to be squared over the area of the second one, which the r is this. So it's going to be pi, and then that is going to be 3r over 5 squared. So that's our area. So now we have pi r squared over, and let's go ahead and square this, that'd be pi times 3r times 3r is going to be 9r squared, and 5 times 5 is 25. Now, what we can do is we can factor out certain things. So we could factor out pi, and we could factor out r squared. And that leaves a 1 up here. So we have 1 over 9 over 25. All right, that's area 1 to area 2. So now, in order to solve this, we need to keep it, change it, flip it. So we just do that. We say 1 over 1 times 25 over 9, which becomes 25 over 9. So we could have tried to use the fact that the ratio of the areas equaled the square of the scale, but we might have ended up with 9 over 25. If we work it out each time, we could be accurate and have a better feel for what we're doing. So always do the keep it, change it, flip it, and work it out all the way. Don't just, put it in your head. Use the cancellation process to find the ratio there. All right, so area 1 is 25/9 of area 2. Or it's 25 to 9, area 1 to area 2. All right, diagonals of rectangular solids. We can use the Pythagorean theorem twice to find a formula for the length of a diagonal of a rectangular solid. And I'm going to show you that in this example problem. Let me clear the page and put that up here for you. All right, in example 510, it asks us to find the length of the diagonal that connects B and H in this right solid. So we're going across from this corner of this box up to the opposite diagonal corner. We're not going from here from B to D. We're going from B to H. So what we're going to have to do is create a new right triangle in this shape in order to find out what this length is. And the way we're going to do that is we're going to first do it in 2 steps. First, we have to find the diagonal from B to G. And so then what that does is going to create a base for us when we find that length that we can then use Pythagorean's theorem to then use Z and compare the two in order to give us a value for BH. Because what we're effectively doing is creating a slice, a new plane within this 3-dimensional shape, right? It just goes diagonal from this corner across to this corner. So that's our new triangle that we're creating. So first of all, let me illustrate the base of this rectangle. The base of this rectangle, we have B and F and G and C. You see that? B, F, C, and G. And between C and G, we have the length Y. Between B and C, we have the length X. You see that base down here? So we're going to find the diagonal from B to G because that is the diagonal direct plane or that BH is on. The BH goes from here up above G, directly above G. So that creates our triangle that we're looking for. So let's find the diagonal BG first. And we're going to do that with the Pythagorean theorem. So we're going to say that the length of BG squared, right, because BG is the hypotenuse in this triangle. See that triangle right here? Let me use my highlighter for this. This is the triangle we're looking at. We're going to find the hypotenuse of this triangle, which is BG. So BG squared is, oops, wrong color, is equal to BC squared plus GC squared. BC squared and GC squared. All right, so that's our Pythagorean's theorem for this. This is the value of BG. Now we need to unsquare everything. And we know that BC is X, so we can rewrite this as BG squared is equal to X squared plus Y squared, because this is X here and this is Y here. Whatever that value is, this is squared and that is squared. And this is the hypotenuse that we have. And so now we are going to unsquare everything, right? This cancels. So BG, the length of BG is going to be equal to the square root of X squared plus y squared, because we can't unsquare those because it's an operation, not factors. Okay? So now the second step is to find the length of the diagonal BH. Now that we have a length for BG, we can attack this triangle here, right? So this is this line here, and it is the square root of x squared plus y squared. And the height here is z. So this step, now that we've done this bit, I'm going to erase this just for the sake of giving ourselves more room. If you need that diagram, go back and draw it or rewind so you can see it. So now we're doing, let me highlight here. So we've done this one, right? We found it. And we know what this one is. This one is z, right? That's z. So now we're going to find this one, the hypotenuse for this right triangle is BH. But we had to find the base of that right triangle in order to find the hypotenuse. Now we can do the same thing, only this time we're going to say BH squared is equal to BG squared plus HG squared. And we know BH squared is equal to BG squared is going to be the square root of x squared plus y squared squared plus z squared. Okay? So we know that these squared cancel each other out. So the radical sign goes away. So the square of BH is equal to x squared plus y squared plus z squared, because the square root of those two added together times the square root of those two added together. We just did this. We said x squared plus y squared times x squared plus y squared, both in the radical. The radicals canceled each other out. So we were left with x squared plus y squared, because we know that that's what that equals. Whatever is in the base when you have the radical with the same index becomes the answer, right? That is the answer. So x squared plus y squared plus z squared. So now we're going to unsquare this side and unsquare this side. That cancels. BH is equal to the square root of x squared plus y squared plus z squared. And that is solved. That is the answer for the length of BH here. Okay? Awesome. So one of the things that you can do is write this down as the diagonal. You're going to need an illustration, but this is something that you can always use. If you have a value here, and you have a value here, and you have a value here, you can find this value here. You can drop that in. You can find BG by taking x squared plus y squared and the square root of that. And then you drop that in with the z squared value to find the diagonal. So definitely write this example problem down. Keep this on handy reference, because then you won't have to start from scratch each time. But it is important to understand where the values come from and how you're doing this. And if you need more explanation on this, please let me know. I'm more than happy to help. All right, so we have one more just like that. Let me clear the page. And we are going to find the length of diagonal AC in this rectangle. All right, let me get my rectangle. I'll show you how I actually pull my rectangles in for these three-dimensional shapes. I bought these cool set of clip art shapes, and I just drag them in, and voila, I have a shape. I'm going to make this a little bit smaller so it doesn't take up as much room. Isn't that easier than me drawing? And it looks so much better. All right, so in this shape, we have this back corner is B here. This is A. This height is M. And the width is 2, the length is 3, and this diagonal across from B, this is C right here. All right, so what we need to do is find the length of AC. That's what we're looking for. So we're going to start with finding, we're going to do the two-step solution, and we're going to find the diagonal we need to find from A to C. So we need to find the diagonal B to C first. So here's our first little rectangle. I'm going to do the base, right? And with the base, we have B and we have C, and this is 2 and this is 3. So we need to find from here to here, this diagonal. All right. We can do that. We've done that before. So this is, if this is 2, then this is 2. So this is our little triangle we're looking at. And we need to find the hypotenuse, right? So we know A squared. So 2 squared plus 3 squared equals BC squared. That's what we're looking for. So 4 plus 9 equals BC squared, and that's going to be 13 is equal to BC squared. We square both of those. This cancels. So the square root of 13 is the length of BC. All right, so that's what this one is. Now we've got to find, so we found this one from here to here. That is the square root of 13. So now we need to find from here to here, this diagonal, right, from above, A, B, and we don't know what M is. We know this is square root of 13, but we don't know what M is. So we'll use the variable M. That's all we can do. So we'll drop in those values. We're looking for the hypotenuse here. Let me use my highlighter. Here's the height. Here's the base. We're looking for the hypotenuse, A to C. So AC squared, that's our hypotenuse, is equal to M squared plus BC squared, because that's the base, which is that diagonal. So that would be the square root of 13 squared. Square root of 13 squared is going to be 13. So AC squared equals M squared plus 13. Right? Easy peasy. Now all we do is unsquare. That's as far as we can go with that. So we unsquare everything and we find this cancels. AC is equal to the square root of M squared plus 13. Or you could have said 13 plus M squared. Either one is correct. But that is the length of AC, which would be that little diagonal from there to there, making that slice of right triangle within our three-dimensional shape. All right. That's all we have for lesson 5. I know that was a lot. If you have any questions, please message me and I'll be happy to help. And I'll see you in lesson 6.